So the last thing we need to talk about is recursive algorithms, recursive methods in terms of big O analysis. Now, kind of just a warning here, the section in this book is it's very much a simplification. Doing big O analysis on a recursive method is probably one of the hardest things you can actually do in kind of the general case. So here, right, these are very much simplified rules that you're going to see, right? And they're going to apply to the things you'll see here, right, in kind of the topics we're covering, but they don't really work for more complicated methods. So when we talked about just loops, right, methods involving loops and nested loops, we had this rule where we said, okay, if I want to figure out what is the big O of that method, well, then I need to find out how many times the loop is being executed, and then how many times something's happening inside that loop, right? What is the big O of the loop, and what is the big O of the body of the loop? And if I did that, if I found those two pieces, then I could multiply them together, and that would give me the big O for the entire method. A similar approach can be used for simpler recursive methods. So instead of doing that, where we're dependent on the loop, what we would do is we would find out what is the big O of the method, in general, right? So something like our sum method, for example, is going to end up being a big O of 1, right? There's no loops in that, right? We just do kind of the same amount of work every time it's called. So the body of that recursive method is O of 1. But then what we do, right, is we multiply that by the number of times you expect that method to be called. While for the sum method, that sum method is going to end up being called n times. So we have effectively n times 1, right? So that ends up being big O of 1, right? We have a growth function of n, big O of 1. So that's relatively straightforward, right, for that particular method. So it's recursive, but if we just kind of multiply things, we find out that it's big O of n. The more complicated case is for something like Towers of Hanoi. So for Towers of Hanoi, actually doing work, moving stuff around, that's very simple, right? There's no loops involved. It's just going to be big O of 1, right? To print out, we're moving something from one place to another. The issue is that in Towers of Hanoi, every time we run that method, we're not calling ourselves just one time, right? That's how sum was working. That's how factorial works, right? Is you just need to do one recursive call. While in Towers of Hanoi, every time you call that move method, right, to move all the disks from one tower to another, every time you do that, you make two additional calls, right? You need to move two n-1 towers to different positions, right? So that's kind of a big difference. So instead of it maybe looking like n, right, or maybe you might think it's going to be 2n, well, actually what you need to think about is that every single time you call it, you're doubling, right? So move one tower, that means you need to move two towers. For each of those two towers you're moving, you need to move two more towers, right? So really it's not, 2n. Really it looks more like n times n times n. Really it looks more like 2 times 2 times 2 times 2 all the way up to n, right? Every time we run, we double the amount of calls we need to use. Because of that, the growth function for Towers of Hanoi looks very different. It looks something like this: f of n equal 2n minus 1. The general process, right, for deriving this is a little bit more complicated, especially recovering that -1 part. But that's the growth function for the number of moves that are required by Towers of Hanoi, right? The number of calls and the number of moves. So if we do big O of this, we get big O of 2 to the n. Well, that's an exponential number. So it's an exponential increase, right, as we increase the size of our tower. So it turns out that even for very small towers, it'll take millions, billions of operations, right, because it has this very fast growth, right, this exponential growth. In general, right, we always want to avoid exponential functions, right, exponential algorithms, right. Those are algorithms that take too long to run, right. We're not going to be around anymore by the time they're done executing. If you have the textbook, I'd recommend you maybe read the last sentence in this section and see kind of the how long it can take. Right, there's a little bit of an interesting story there. So that about wraps up this chapter. Overall, right, we've talked about recursive thinking, right, recursive data structures, a couple of very easy functions to use recursion, and then we did the maze and this Towers of Hanoi example, right, as kind of a more complicated things.